Let's make sure it's filming and not taking a picture. Okay. All right, inside our nucleus are two main things. They are the protons and the neutrons. Okay, protons you can write as a symbol of a little p with a plus sign because they have a positive charge. Neutrons you can write as a symbol of a little n with a 0 up top because they are neutrally charged. Now, between our protons and neutrons, in terms of visualizing their size, they are relatively the same size. So protons and neutrons are about the same size and mass. If you get down to the details of it, they're not exactly the same by mass, but for our level of chemistry, it's pretty much the same. You have to go out like 5 decimal places before it varies. Okay? Now, we've learned before already, so can someone by raising hand for a smiley face remind us, how can I find the number of protons of an atom? How do I find that, McKay?
It's the element number on the periodic table.
Perfect. So when we look at the periodic table, the number up top right here, that tells you how many protons are in an atom. That number by name is also called the atomic number. And it equals the number of protons. Always. Keep in mind that the proton number is like its DNA. You change the number of protons and you change the element. Right? That's like on Iron Man 2, like we talked about before, that's how he made a new element, is by adding more protons to something that already existed. Same idea right now, we have created up to element 118. So in the nucleus level, what do I have to do to just make a new element? Yeah, I just get OG and throw a proton into it. And that's how, in a sense, we would make a new element.
Wouldn't that mean we technically discovered some way of fusion if we can make these new elements?
We have, yeah.
It's just implementing it to make power is very
Yes,
hard.
the power source is the harder part. Yeah. But the reason why it's not as easy as it sounds is because of that video we watched, right, with the big buff protons and the nerdy neutrons. Like, when you start throwing things into a nucleus, they don't always stay together. So that's why it's hard to create new elements. Okay. Someone remind us, we've talked about this one before. How do I find the number of neutrons?
It's your atomic mass, not your atomic number.
Ooh, very close, Seth, very close. Have a smiley face for it. It's not the atomic mass, but it is what's called the mass number. So if you take protons plus neutrons, it equals what is known as the mass number. Now here's the difference that we want to make. This number down here, this 14.007, is not the mass number. It's what's known as the atomic mass. Since mass number is protons plus neutrons, it always has to be a whole number. Because you can't have 0.007 of a neutron or of a proton. Now they can be similar to each other, but the mass numbers, there's lots of options. Atomic mass, there's only one. For example, we said with carbon can be carbon 12, it can be carbon 13, or it could be carbon 14. Those are what we would call isotopes of carbon. They're all carbon, but they have different masses. The atomic mass is found, and we'll learn how to do this later on, by averaging all of the types of mass numbers it could be. So there's lots of these, but when you average them, That's how you get that number. But they are not the same thing. If a problem asks for the mass number, it wants to know how many protons and neutrons are in the nucleus together for that specific isotope. Okay? Okay, so we know how to find protons now. We know how to find neutrons. Let's go over to electrons. So electrons are negatively charged. So their symbol is a little e with a negative up top, because they're negative. Now, electrons do not contribute significantly to the mass. They are matter, they do have mass, but in comparison to protons and neutrons, it's like insignificant, right? So in a sense, this model is very wrong because it makes it look like protons, neutrons, and electrons are all the same size. They're not. If protons and neutrons were like bowling balls, so visualize that, an electron is like a grain of rice. They are teeny tiny in comparison, and so that's why they're not part of the mass. Because it's like you stepping on a scale, and then I like pull a hair off your head. Is your mass really change? Not really, right? A little bit, but not enough to care really, okay? What they do affect, though, is the charge of the atom. Atoms can be neutral, or they can be positively and negatively charged as a whole. So if you take into account protons, so you take the number of protons that you have, and you subtract the number of electrons that you have, that will equal the charge of your atom. And we'll do an example of how to find that, since that's our main new one today. So we take protons minus electrons, you can find the charge of it. Any questions on those so far? Okay, let's watch a short little cartoon to kind of put this all together, and then we'll do some practice problems. Okay, so we now understand how small are atoms? Really, really small, right? And then atoms are made up of protons, neutrons, and electrons, which have to be even smaller. Like they didn't even give an analogy of how small they are, because, you know. Now here's what's crazy, and we're not gonna, this is just so you know, because I want you just, the more knowledge I can give you, the better. Protons and neutrons are made up of smaller things.
Of course they are.
Yeah.
I was pushing that. I was like, is it smaller than
Now this is actually pretty new. Let me go on to the next one here. We have these things, everybody, called quarks. Okay, so scientists have discovered, and you don't need to know this, we're not going to learn about it, because to know about quarks gets into quantum physics, which we're not going to cover in this class, too much at least. But I do want you to know, so that if one day you find this out, you don't think I held back knowledge from you. You can break down protons and neutrons into smaller things called quarks. These are the names scientists have given them. There's up quarks, down quarks, charm quarks, strange quarks, top quarks, and bottom quarks. And then you combine those in various ways to make protons, neutrons, electrons. The craziest thing about chemistry, even for me guys, is the more I learned chemistry through college, the more I realized I know nothing. There's so much to this world of the atoms that we are still figuring out. And that's one of the coolest things, is you are part of some of these discoveries and some of the new things being made. Yeah, Jeff?
Do you think that there's stuff even smaller than that?
Yeah, they're like.
Yeah.
There's a theory a theory that does it that makes it like the smallest, tiniest bit of energy. It's like a vibrating string of energy, and if you were to take an atom and expand it to the size of our universe, or not our universe, our solar system, that string would be the size of a tree on Earth.
Yeah, it's nuts. So crazy. Okay, now taking it back to something we can maybe comprehend. Okay? So when we use this word isotope, everybody, keep in mind that means they're the same element, but different masses. So carbon-12 is an isotope to carbon-14. Same element, different masses. This should be a review from last unit. Top numbers of symbols are always the mass number. The bottom number tells us proton number or atomic number. Okay, so these symbols are just like the symbols we did before in our last unit when we had to balance out the equations. The other way you can also see these things is as the name. So this is known as a nuclear symbol. So the problem says write the nuclear symbol. It should look like that. The one thing that might change from our last unit is there could be right here a charge listed. If the atom is not neutral, we would write its charge here. If it's neutral, then there's nothing. Okay? We can also write it as the name, which the name is always listed as carbon dash the mass. Yeah, Sam.
So neutrons have nothing to do with the charge, it's just the protons and the electrons?
Yes. Yep. So the mass is all about protons and neutrons. The charge is all about protons and electrons. So.
And if electrons are so small, why do they have an equal charge, like an equal negative charge to the
To a proton?
positive?
Yeah, great question. It's that charge, and we'll understand charges better as we go throughout the year. A charge is not dependent upon mass. Like you can have something really, really small with a -1 charge because it's not a measurement of its weight or size or in any way. So, great question. Okay, let's go ahead and try a practice problem right here. So this is similar to like what we'll be practicing on our homework tonight. I've given you an isotope, and we need to identify these different parts of it. Okay? So our isotope is chlorine-37. First thing I always find if I can, because it's very defined, is the atomic number. So how do I find the atomic number?
17.
Very good, looking over there. So chlorine has an atomic number of 17. This, once I found it, is a 2-for-1 deal. Because these two things are always the same. So if you know the atomic number, we know the proton number. How do I find the mass number?
37.
Good, Bell's pointing right here, 37. This is just given. Keep in mind, this is not found on the periodic table. If it wasn't given to you, the only other way to find it would be they would have to give you the neutrons. You have to be given one of these two things, otherwise you're stuck. Now, what's the relationship of neutrons with the mass?
The mass times added.
Good, so this and this add up to be the mass. So if I take mass minus protons, so what does that give me, 20? I can find my neutrons. Keep in mind that all the mass of a nucleus is in that, all the mass of an atom is really in that nucleus. Right? The video talked about how dense that nucleus is. Okay, now electrons, the equation that we have is that protons minus electrons will equal the charge of our isotope. Now, if nothing is listed, and I'll show you what it looks like when it is listed, the charge is just 0. So in this case, our charge is 0.
17.
So that means it has to be the same. So my number of electrons is 17. These two things will be the same. So protons and electrons are the same if the charge equals 0. Because in order for a charge to be 0, you have to have the same number of positive things as you do negative things. Okay? All right, now let's learn how we can draw a picture of this particular isotope. So we're going to learn what are known as as Bohr's model for an atom. Now with Bohr's model is probably the most common model of an atom you've seen up to this point. This right here is Bohr's model. The idea of you got the nucleus in the middle, and then you have these rings, orbits, shells, energy levels, whatever you want to call them, around the outside. The thing about Bohr's model that's interesting is there's a lot that is wrong about Bohr's model. This is not what an atom looks like. But it's a good starting point to understand how the atom is structured. So we'll learn next time about the history of the atom and how Bohr was just a piece in getting us there. The other reason is it's the easiest to draw. After Bohr, the models get extremely complicated to draw. So at this level of chemistry where we need something to visualize, because that's important, we're starting with Bohr's model, okay? Now, the rule with Bohr's model, and this is true for outside of it, there's a max number of electrons that can dwell on each energy level. Okay, so they can only hold so many. So level 1, inside the atom, does anyone know how many electrons it can hold? 2. So that's the max it can hold. Okay? The second energy level can hold 8. Now, this is where you may have been told something in 8th grade because you were only in 8th grade, and I don't know why they tell you this, but it is what they tell you. Level 3 holds 18. The number 8 plays a magical role in chemistry, and so that's why it's emphasized in the earlier years of learning it. But once again, it's not true. The 3rd level can hold 18. The 4th level, and that's as big as we'll go in this class, can hold 32. There is a pattern in a weird way, McKay, but we won't learn that for a few more units. Yeah?
Then why does it say 8 up there on level 3?
Great observation. So, over here, if you haven't noticed, you can find these numbers actually written in black. 2, 8, 18, 32. Now, I don't know if this might not answer your question all the way, Sam. It'll make more sense once again when we learn about something called electron configurations. The reason why it just shows right here the 3rd row is the 3rd row doesn't contain everything that can fit on the 3rd shell. It's some of it, but it's not all of it. So, great observation though. Okay, so that's as big as we'll go. So now when we draw a picture of this, I'll draw it right here. The first thing we do is we draw the nucleus. Now for the nucleus, all we're going to do is just list how many protons and neutrons there are. So we'll put 17 protons and what do I got? 20 neutrons. Draw a circle around it. There's your nucleus. Now we need to place 17 electrons on the rings. So for the first ring, it can only hold 2. Now you have 2 options here for electrons, and this is just personal preference. You can either draw them, so I'll draw 2 pictures so you can pick which one you like. Whoops. Okay, so you can either draw them as dots, or you can write it like this and just write the number. If you like drawing dots, draw dots. If you want to write a number, write a number. Okay, so first ring's going to hold 2. Second ring can hold up to 8. Now the third ring can hold up to 18, but don't get carried away, because how many more do we need for chlorine? Yeah, we only need 7 more. Because these 3 numbers right? This should add up to how many electrons we have total. So don't go electron crazy and just keep going, right? Questions on Bohr's model or other questions, Carter?
So how does the levels and ratings apply to an electronic lab?
So when we get into, once again, electron configuration, we'll learn that there's,
Because I see in the pictures it's less dense in the middle, so is that where there would be two?
yes, yep, so it's all about probability factor, right? That's the modern view. It's we can't specify exactly, but the highest density probability is in that area, the first energy area, only 2 electrons will dwell there. So, any other questions so far? Yeah, Jeff.
I didn't quite understand when you were answering Sam's question with the y on the periodic table. What is 8 for level 3?
So here's the best way I can say it for now, and once again, it'll make more sense in a later unit when we learn about it. So these 8 elements are all part of the 3rd energy level, but actually so are these 10. So that's where you get your 18. For the 4th, these 2 are part of the 4th, these 6 are part of the 4th, these 10 are part of the 4th, and these 14 are also part of the 4th. So when you add all those up together, you get your 32. Does that kind of answer it for now?
That's a good point.
Might be like my broom. I lost my stick. I had at least a yardstick to point with. But okay, any other questions? Okay, flip your paper to so there's 2 more slides we're going to skip for now. But just go to that blank space and we're going to do another one for some smiley faces. So we're just going to do a practice problem and some smiley faces and check how we're doing. Okay, so if I give you, so I'm going to give you the isotope symbol, and then you're going to tell me all these things about it, okay? Okay, let's do arsenic. So I want you to tell me its atomic number, mass number, proton number, electrons, and neutrons. And you can have a smiley face for everyone you get right. So that's up to 5. Okay, ready, set. You can talk to your table buddy if you want to. Go. When you're done, set your pencil down so you know you're finished. One thing, even if you don't know how to find all 5, find the ones you can find, because then we'll know what we have questions with still. Let's do 2 practice problems. So after you do that one, do the same thing for this. Everyone you get right, you can have a smiley face. Okay? All right, atomic number is 33, which tells me proton number. Okay? I always try to find protons first because it's normally the simplest. Okay? Mass number is given, 71. So then, since I have these 2 things, I then go to my neutrons next, because 71 minus 33 gives me my neutrons. So 38. Now, electrons are dependent on the charge. Now, there's 2 ways you can kind of think about it if you want. Here's how I think about it, okay? Electrons are negative, protons are positive. If we have a negative charge, that means we have more negative things than we do positive things. And in this case, we have 3 more negatives than we do positives. So since my protons are the positive, and there's 33 of them, that means I have 36 negative things. Because these are negative and those are positive, and together, they have to equal the charge. Questions on that one? Okay, on this side, atomic number would be 20. Proton number would be 20. Mass number is 41. Minus that away, so 21 would be my neutrons. Now, it's positive, so that means I have more protons than I do electrons, so 18. Questions on any of those? I hope that electrons are the hardest thing for you to find right now. If that's the hardest, that's an okay thing for to struggle with, because that's mostly what was new today. So as you practice it, you should get better at it. But yeah, question, Mia?
Can you explain how you got the 18 one more time?
Yeah. So I know the charge is +2, and so these things are my positive things, and these things are my negative things. So together, they have to equal +2. So 20 plus -18 gives me the +2. Does that make sense? Same thing along on this side, 33 plus -36 would give me the -3. So, no, good clarification. Any other questions? Okay, take a look at that homework packet I just gave you. There are